Sequences are complicated. It's not so easy to find the limit of a sequence. The logistic map provides one source of rich, and by rich I mean very complicated examples. Let's see how these are defined. Here's a sequence I want to consider. It's actually a family of sequences which depend on some parameter r. Let's call r 2.5 for the time being, and I'll pick an initial value for my sequence. Let's make it 0.25 for now. And then here's the recursive definition of the sequence. A sub n plus 1 will be this constant r times the previous term a sub n times 1 minus a sub n. And by varying r and by varying the initial value, I'll get a whole bunch of different sequences to consider. Let's try it with those values. Let's try it with r equals 2.5. So here's an example. I start with the initial value 0.25, and each subsequent value is 2.5 times the previous value times 1 minus the previous value. And here I've graphed these values, right? The first is at 0.25, then it goes up a bit, and then it goes up, and then it starts sort of leveling off here. And indeed, if we look at this numerically, right, the first value is exactly 0.25, and then as I run down through this sequence, it seems like the values are getting closer and closer to about 0.6. And in this case, the limit of this sequence is in fact 0.6. What if we start with a different initial value? What if instead of a sub 1 equals 0.25, we make a sub 1 equal something else? So the recursive formula that we're using is a sub n plus 1 is 2.5 times a sub n times 1 minus a sub n. And before we were starting with a sub 1 equal 0.25, let's start with 0.8 and see what happens in that case. So if I start with 0.8, I could rewrite 0.8 as 4/5. And then instead of writing 2.5, I'll write 5/2 times an times 1 minus an, just so I can work with the fractions instead of the decimals. So let's use this to calculate the next term. What's a sub 2? Well, according to this formula, it's 5/2 times a sub 1 times 1 minus a sub 1. But I've got a sub 1, it's 4/5. So that's 5/2 times 4/5 times 1 minus 4/5, which is 1/5. Now 1/5 and this 5 can cancel. I can get rid of these. And this 4 and this 2 become a 2 in the numerator, so I've just got 2/5. So a sub 2 is 2/5. Now I can calculate a sub 3. So a sub 3 will be 5/2 again times a sub 2 times 1 minus a sub 2. And in this case, what is a sub 2? We just calculated it's 2/5. So this is 5/2 times 2/5 times 1 minus 2/5, which is 3/5. But now I've got 5/2 and 2/5, and those cancel. So a sub 3 is just 3/5. Now let's calculate a sub 4. Well, a sub 4 is again 5/2 times a sub 3 times 1 minus a sub 3. That's 5/2 times a sub 3 is 3/5. 1 minus 3/5 is 2/5. But now I've got 5/2 and 2/5. Those cancel, so a sub 4 is just 3/5. Well, what's a sub 5? Well, a sub 5 is also 3/5. I'm going to use the exact same formula here, but I'm again just going to plug in 3/5, and I'm going to get 3/5 out. So a sub 5 is 3/5, a sub 6 is 3/5, right? The point is that this sequence is just constant from here on out. And that means that in this case, the limit as n approaches infinity of this sequence is just 3/5. Just like in the case when I started with 0.25, right? It happened in this case that even when I started with 0.8, when I used this formula, I again ended up with the same limit. It's kind of interesting. Let's try r equals 7/3. I'll again have my sequence start with 0.25, but then each new term is 7/3 times the old term times 1 minus the old term. And if we look at this graph, it looks like this sequence is converging. And if we look at the numbers, right, the first term in this sequence is 0.25, then it's about 0.4, then about 0.57, and it keeps on going. And it does indeed look like this sequence is getting closer and closer to something. This number might not be too meaningful to you, but you can in fact show that the limit of this sequence is 4/7. And indeed, this number is about 4/7. So changing the value of r seems to affect the limit. Let's try r equals 3.25. So again, my sequence will start with 0.25, but now the r value is 3.25. What does this sequence look like? Well, I can graph a bunch of terms of this sequence, and it starts at a 0.25 and it goes up, and then it seems to bounce between two values. And indeed, the numerical evidence supports that same conclusion. Here's the first value, 0.25, and it's about 0.6, 0.7, 0.5, 0.8, 0.5, 0.8, 0.5, 0.8, 0.5. And it seems to just be flip-flopping between these two values. And since it's flip-flopping between those two values, the limit doesn't exist. Let's try another example. Let's try r equals 3.7. So same initial value, 0.25, but now 3.7 is my value for r. What does this sequence look like? Well, I can start graphing the terms in this sequence, and wow, I mean, it just looks like garbage. There just doesn't seem to be any pattern at all. You know, and there's maybe moments when it looks like things are getting better, but then it suddenly breaks apart again. And if you look at the numbers, right, numerically, things don't look so great here either. I mean, 0.25, that's the initial value, but as you look through these numbers, it doesn't look like any sort of pattern is really coming out. What is going on here? Well, changing the value of r doesn't just change quantitative features of the sequence. It changes qualitative features of the sequence. Depending on the value of r, this sequence might converge, might have a limit. It might flip-flop between a couple values. It might flip-flop between 4 different values. It might just move all over the place and not really have any kind of discernible pattern. And it all boils down to this value of r in a seemingly mysterious way. But that's not to say that the sequence can't be understood, that it can't be studied, right? Math isn't just random, right? I mean, there's structure to this thing. And with more work, you can really start digging into the very complicated structure that appears even in something as seemingly simple as just a sequence of numbers.